Hello and welcome back. In this video we will look at more about symmetry. And we were just introduced to the idea of symmetry about the y-axis, the x-axis, and the origin for a graph. So if we're given an equation that describes a graph, we can then ask, okay, does this have these sorts of symmetries? So remember that y-axis symmetry means that when we reflect about the y-axis, so when we exchange left and right, so say positive x values and negative x values, we should get the same thing. So what we'll do is we'll take our function, we'll take our equation and we'll replace x with negative x. So nothing happens to the y. X becomes a negative x. So instead of x squared, I've got negative x quantity squared minus 1. And here, again, the y doesn't change. The negative x squared, well, negative x times negative x, the negative signs will cancel out, and I'll just get x squared minus 1. And I have the same equation as the top line. This means after I exchanged x and negative x, I got the same graph. So this is symmetrical, and it's symmetrical about the y-axis. We should check more as well. So here with the x-axis, we will also look at whether or not this is going to be symmetrical about the x-axis, meaning if we exchange the top and bottom, so up and down. So what we'll do is we'll exchange a y with negative y, and we'll look to see if we get the same equation. What I'm going to do to make this a little bit simpler is I'm going to divide both sides by negative 1, so I can cancel out that negative sign, and I will get negative x squared plus 1. And when you look at the original equation and this bottom equation, we've got y is equal to x squared minus 1, y is equal to negative x squared plus 1. These aren't the same function, so it's not symmetrical about the x-axis. The last one is the symmetry about the origin, which is the rotational symmetry, rotating it halfway around. And to do this, we exchange, we look to see if we get the same graph if we exchange x with negative x and y with negative y. So let's make these exchanges. Y becomes negative y, x becomes negative x. And when I multiply this out, I still have the negative y. Negative x squared, again, the negative signs cancel out, and I just get x squared minus 1. And just like before, I'm going to divide everything by negative 1. Just change all these signs, so I get y is equal to negative x squared plus 1. So my equations don't look the same. Y is equal to x squared minus 1, y is equal to negative x squared plus 1. These aren't the same. It's not symmetrical about the origin. So when we actually graph this, so our equation is y is equal to x squared minus 1, we get the following. This is a parabola. It'll pass through the point 0, negative 1, negative 1, 0, and 1, 0. So it'll look something like this. We will see this in later chapters as well. We'll learn how to graph parabolas. And what we notice is that, yes, this does have the y-axis symmetry. If we draw this, if we highlight the y-axis, if we flip the graph over in this way, we still get the same thing, but not if we flip from top to bottom, and not if we rotate 180 degrees. So this has y-axis symmetry, but not x-axis symmetry, and not symmetry about the origin. Let's look at another graph. So again, this is given by an equation. This is x squared plus y squared is equal to 1. For y-axis symmetry, I'll need to see if I get the same graph if I exchange left and right, as in if I exchange positive x values for negative x values. So when I make this exchange, I get the negative x squared plus y squared is equal to 1. And just like before, negative x times negative x is going to be x squared. The negative signs cancel out. So we get the same equation and it's symmetrical about the y-axis. If we keep going, symmetry about the x-axis means we're exchanging up and down, so we're exchanging positive y values for negative y values. And when I do this, when I write a negative y instead of a y, again, negative y times negative y, the same thing that happened with the x, the negative signs will cancel out. And I'm left with the same equation again. So not only does this have y-axis symmetry, this also has x-axis symmetry. And for the same reasons that everything canceled out before, for symmetry about the origin, if I replace x with x minus x and y with minus y, all of the negative signs will cancel out. So negative x squared, well, that's just x squared. Negative y squared is going to be y squared. And everything's equal. So this graph has all three types of symmetry that we've talked about. So this is going to be a highly symmetrical object and one very symmetric shape. This is in fact the circle. Maybe poorly drawn, but it satisfies this equation. So again, you can see that if we were to flip the circle over from left to right, say across the y-axis, we have the it still looks the same. If we flip it top to bottom across the x-axis, it still looks the same. If we rotate it, it doesn't matter how much, but if we rotate it say 2 quadrants around, it's still going to be the same. So the circle has lots and lots of symmetry. So what we've been looking at before have been graphs, and now we want to look at symmetry in functions in particular. So remember that every function will correspond to a graph, but not every graph comes from a function. So even functions are give graphs that have symmetry with respect to the y-axis. And it turns out that there's an equation that we can look for to see, and this is given by this equation here. The way we check to see if a function is an even function and if it has symmetry about the y-axis is we replace x with negative x, and we see if we get the same values out. So again, y-axis, we want to flip left and right, so we exchange x and negative x. So here's a function, f of x is equal to x squared. So let's try plugging in negative x into our function, and what we'll have is negative x quantity squared, and we get x squared. And we look at this and we go, oh, wait a second, this is actually the same thing as our original function. So yes, this has symmetry about the y-axis. And if we were to graph this, we would be able to see the same thing. This is a parabola. Again, you can flip it across the y-axis. Here's another graph. F of x is equal to 2x. So what we'll do to check to see if this is an even function, we'll plug in negative x, and what we'll get is 2 times negative x. And 2 times negative x will be the same thing as, if I pull out that negative sign, negative 2x. But these two things are not equal. This is not the same thing as f of x. This is positive 2x, this is negative 2x. They're not the same thing. So whereas before we had an even function, this is not an even function. And if we were to graph 2x, 2x is a linear equation, linear polynomial. So we get a linear line. It should pass through the origin, if I can draw correctly. But if we flip this over the y-axis, we're not going to get something that looks right. This is an increasing function. If we flip this over, we'll get a decreasing function. So this is not even. The next type of function, as you might expect, if we have even function, we'll have odd functions. And odd functions are functions with symmetry with respect to the origin. So these are the rotational symmetry. And the way that we check this is we'll look to see if f of negative x is the same thing as negative f of x. And roughly what this amounts to is both exchanging x and negative x and y and negative y. But I won't go into these details. I'll just look at doing some examples with that. So here we have f of x is equal to x squared. So one thing that we want to check is f of negative x. And we already did this calculation before. This is negative x squared. Negative signs cancel. And then the next thing I want to do is I want to look at negative f of x. Well, negative f of x is just going to be negative x squared. And we see that these two are not equal. So to be an odd function, f of negative x has to be equal to negative f of x. f of negative x and negative f of x are not equal. So this is not odd. So again, this is a parabola. And we can see that this does not have the rotational symmetry. So this is not an odd function. It doesn't have symmetry about the origin. Here we've got our other function f, say negative 2x. So what we can do is we can plug in negative x. 2 times negative x is the same thing as negative 2x. And this is already looking good. If I try negative of my original function, I get negative 2x. These two guys are the same thing. So f of negative x and negative f of x, those are equal. So therefore this is odd. And again, if I draw the graph, this is going to be a straight line passing through the origin, and when I rotate this by 180 degrees, I'll get the same thing. So this graph has symmetry with respect to the origin, so therefore this is an odd function. Just by looking at these graphs, we can tell whether or not they're even or odd or both or neither. So for instance, here for this first graph, if we flip this over the y-axis, we get the same thing. So this is in fact even. But this doesn't have that rotational symmetry. So it's not odd. This one, if I reflect it across the x-axis, I don't get it. Don't get it back, and it doesn't even have rotational symmetry. So this is not even, and it's not odd. So you can have graphs without any symmetry, like this one, or this last one. I can't reflect this about the y-axis because then this on top would end up over here, so it's not even. But this is odd. I could spin this around and get this to land on top of itself. So this is an odd function. So we have an example of even but not odd, not even and not odd, not even and odd. A circle would be both even and odd with this. So one thing I want to do is I want to quickly point out that for polynomials, there is a pretty quick way of seeing if something is even or odd. Here we've got x squared plus 6, and one thing I could do is plug in a negative x into here and see that negative signs cancel, or I could do the following. X squared, I'm not going to simplify, but 6, I can write this as 6 times x to the 0 power, remembering that x to the 0 power is just 1. So when I look at this, I look at each power of x. That's an even power. 2 is even. 0 is even. So this is an even function and not odd. Over here, when I look at these powers, I have an odd power, and x by itself is just x to the first power. So this is going to be an odd function. But this last guy, x to the 5th plus 1, well 1 is 0. I've got a mix, 1 even, and 1 odd. So this is neither even